Welcome back. In this section, we're going to be talking about some more trig identities. These ones are the double angle identities, sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. The good news is that all of these identities really just come from the angle sum identities from the previous section. So for example, sine of 2 theta, to find the identity for that, I just realized that sine of 2 theta is sine of theta plus theta. And now I just have to use the formula from the previous section. Sine of the first angle, cosine of the second, plus cosine of the first angle, sine of the second. And since our first angle and second angle are the same here, then we've got two identical terms. We've got a sine theta times a cos theta twice over, so 2 sine theta cos theta. Now I'm going to do the same sort of a thing here for the cosine of 2 theta formula. That'll be the way that I'll generate the first double angle identity. I'll start off by saying that cosine of 2 theta is, just like I did for sine 2 theta, it's cosine of theta plus theta. And I can say that is cosine of the first angle, cosine of the second, minus sine of the first angle, sine of the second. And since the angles are the same, theta and theta, then the first part, cosine times cosine, just turns out to be cosine squared theta. And the second term, sine theta times sine theta, gives me sine squared theta. And there we go. That's my first of my three identities. The second and the third one, I really just get those from taking my first identity and using a Pythagorean identity to rewrite it. So we already have just shown that cosine of 2 theta is cosine squared minus sine squared. And if I were to replace the sine squared with a 1 minus cosine squared using my Pythagorean identity, then that will simplify to give me 2 cosine squareds minus 1. And that's my second of my three second of my three cosine double angle identities. The third one I get, instead of replacing the sine squared, I get it by replacing the cosine squared. So I start off as cosine of 2 theta being cosine squared minus sine squared. And then I say to myself, I'll replace the cosine squared with a 1 minus sine squared theta. And then that's just going to simplify to give me 1 minus 2 sine squared thetas. And there we go, our third double angle identity for cosine. Okay, so now let's use these identities. Here I've got an angle in quadrant 1. I know the value of tangent of theta, and I want to find cosine of 2 theta. And a lot of people will think that if I'm looking for cosine of 2 theta, I'll first need to figure out what actually is angle theta. And the good news is we don't know what angle theta is, and we don't need to know what angle theta is. I'm actually going to start off really doing the same sort of thing that I did back in chapter 7. If I told you we had an angle in quadrant 1 and tangent theta was 5/12, then I would have drawn my angle in quadrant 1. And I would have said, since tangent is 5/12, and I know tangent is the y value divided by the x value, then that means that for that angle that I've just drawn, that there's a point on the terminal side where the x-coordinate is 12 and the y-coordinate is 5. And I can use that to figure out what r is. I know that r is root of x squared plus y squared. And so if I put in what I have for x and for y, 12 squared and 5 squared, that's 144 and 25, and that adds up to 169, and that's a nice perfect square. Square root of 169 is 13. So now I know the values of x and y and r, and I can use that to figure out what cosine of 2 theta is. Because remember, cosine of 2 theta really could be written in terms of sines and cosines. Cosine of 2 theta is cosine squared theta minus sine squared theta. And we know how to find cosine. Cosine is the x value divided by r. And we know what the x value is. It's 12. And we know what the value of r is. It's 13. So cosine theta is 12/13. So we've got 12/13 squared. And then same thing for sine of theta. Sine is y divided by x, and y is 5. Sorry, y divided by r, rather. Y is 5, and r is 13. So sine of theta is 5/13. So we've got 5/13 squared. And then the only thing left for me to do is just a little bit of arithmetic here. So 144 over 169 minus 25 over 169, which gives me 119 over 169. And there we go. That's our exact value of cosine of 2 theta. And notice again, I didn't need to know what the angle theta actually was. I didn't need to find out what is that angle. If you tried to, it wouldn't be a nice angle. You wouldn't be able to find the exact value anyhow. And good news, you don't need to find that angle to find out what cosine of 2 theta actually is. Now, of course, we can also use these double angle formulas to establish new identities. So here on the left, I've got sine of 2 theta on the top and cosine of 2 theta on the bottom. So not a surprise, I'm going to need to use those double angle formulas at some point. And hopefully once I do, things will clean up to give me just tangent of theta on the right-hand side. So I'm going to start off with my left side being sine 2 theta over 1 plus cos 2 theta. And for the numerator, that's the easy one because there's only one sine identity for the double angle. That's 2 sine theta cos theta. So the numerator, I already know what I'm doing with that. The denominator, I'm going to need to take a minute to think about it. And so if I'm looking at this, I know that on the right-hand side, I have tangent. And I know that tangent is the same thing as sine divided by cosine. And I see in my numerator I have a sine with an extra cosine and a 2 lying around that hopefully I'll be able to get rid of. So I'm hoping that maybe the bottom I can turn it into something just involving some cosines that will allow me to cancel out the cosine that I have on top, hopefully leaving me with a sine divided by cosine, which I'll turn into tangent. So I'm looking at my denominator, 1 plus cosine of 2 theta, and I'm thinking, well, okay, I need to use a double angle formula, and hopefully that 1 needs to go away. So that's where I'm thinking about, well, if I were to use the double angle formula for cosine of 2 theta, that is 2 cosine squared theta minus 1, then the 1 and the minus 1 would cancel each other out, and hopefully that would lead me to somewhere closer to where I wanted to be. And so when I do that, I can see that actually, yeah, that does seem to be working for me because now in the numerator, I have 2 sine theta cosine theta, and in the denominator, I've got 2 cosine squared thetas. And I can see that actually everything's unraveling pretty nicely here because the 2 and the 2 are going to cancel. And of the cosines, I have 1 on the top that can cancel with one of them that's on the bottom. So it looks like, yes, things have simplified down to just being sine theta over cosine theta, which is indeed tangent of theta. That is my right-hand side. So that means I've accomplished what I wanted to do. I've shown that sine 2 theta over 1 plus cosine 2 theta is equal to tangent of theta. And there we go. Let's do another one here. This is another one of finding an exact value. And again, same as before, we don't have to worry about what exactly is the angle theta. We are going to use our sine formula, and I know that if I wanted to find sine of 2 theta, that is 2 sine theta cosine theta. So as long as I can find sine of theta and cosine of theta, I should be fine and good to go. So that's what I'll do here. I'll first start off by drawing my right triangle. And I've got my angle theta. And I know since tangent is 1 over 5, and tangent is opposite over adjacent, then I can say that for this triangle that I've drawn, the opposite side should measure 1, and the adjacent side should measure 5. And, of course, I can find out what the hypotenuse is. I know that the hypotenuse squared would be 1 squared plus 5 squared, which is 1 plus 25, or 26. And when I'm taking my square root, I know that the hypotenuse, since it's a length, it has to be a positive number then that means the hypotenuse is the positive root of 26. And that doesn't need to be simplified any further. Root of 26 has no perfect squares that go into it. Okay, so we know our opposite side, we know our adjacent side, we now know our hypotenuse is root of 26, which means we're ready to answer our question about what is sine of 2 theta. So we can say sine of 2 theta is 2 times sine theta times cosine theta. Sine theta should be the opposite over the hypotenuse, and cosine theta should be the adjacent over the hypotenuse. And that's going to clean up pretty nicely on the top. 2 times 1 times 5, which is 10. And on the bottom, root 26 times root 26, which is just 26. So we have 10/26, which simplifies to give me 5/13. And there we go. There's our exact value of sine of 2 theta. Okay, so we've identified most of our double angle formulas already. We've looked at sine, we've looked at cosine. The only one left is tangent, and for tangent, there's 2 ways you could find that double angle formula. One is if you remember your if you remember your angle sum formula for tangent, you can do it the same way that we did for sine and for cosine, saying that tangent of 2 theta is tangent of theta plus theta. And the tangent formula for 2 angles added together is tangent of the first angle plus tangent of the second angle over 1 minus tangent of the first angle times tangent of the second angle. And of course, since the angles are the same, then on the top you have a tangent of a theta plus itself, or 2 tangent thetas. And on the bottom you've got 1 minus tangent times itself, or 1 minus tangent squared. That's if you remember the formula for tangent, but good news is you don't have to remember the formula for tangent of angle plus itself. As long as you know the formulas for sine and cosine, you're still good to go, because we know tangent of 2 theta is sine of 2 theta divided by cosine of 2 theta. And we already know the formulas for those. Sine of 2 theta is 2 sine theta cosine theta. And cosine 2 theta is cosine squared theta minus sine squared theta. And to turn this into a bunch of tangents, the only thing I would need to do is take everybody top and bottom and divide them by cosine squared. And that's because on the bottom, that would give me cosine squared and cosine squared canceling, leaving 1. Sine divided by cosine, that is tangent, so sine squared divided by cosine squared, that should be tangent squared. And on the top, cosine cancels with one of the cosines, and you are left with 2 times sine divided by cosine, or 2 times tangent. So either way, if you know the formula for tangent of one angle plus another, then you can easily find the double angle formula for tangent. But even if you don't, you could just use the sine and cosine formulas instead, and then do a little bit of extra work to get there. There's a couple of other formulas that are maybe less important for this class, but will become important later on in calculus. There'll be some times where you'll have some power of sine or some power of cosine, and you'll need to rewrite it without having a power on it. And for that, you're going to be using these power-reducing formulas that I have up top. So for these, you'll notice that something involving sine squared could be written in terms of cos 2 theta, no longer having a square in it, and things involving cosine squareds could be written in terms of cosine 2 thetas again, no longer having a square. And both of these formulas really just come from the double angle formulas for cosine. Because you know, for example, cosine of 2 theta was 1 minus 2 sine squared theta. And if we just move everybody from one side to the other, so moving the 2 sine squared to the other side, moving the cosine of 2 theta to the other side, and then dividing by 2. And same sort of thing for the other power-reducing formula, the one involving cosine squared. I start with my cosine 2 theta formula, this one with cosine squared in it, so 2 cosine squared minus 1. Move the 1 to the other side. Divide by 2. And I've got cosine squared theta is 1 plus cosine of 2 theta all over 2. And so there we go. I've got my two little power-reducing formulas. And I'm going to do a quick example of that just to show how even if the power was bigger than a power of 2, you could just use the power-reducing formulas a couple of times or a few times in a row and reduce it down to something where there are no more squares and no cubes and no higher powers, where the highest power on any cosine or sine function is just a power of 1. So let's do an example of that. We've got sine to the power of 4x, and I want to make sure that I don't have any higher powers. I don't want any squares or any other higher powers. So when I do that, I'm going to first start off by saying I know sine to the power of 4 is sine squared times itself. And I have my power reducing formulas for sine squared. So I can start off with that and say, well, sine squared x is 1 minus cosine of 2x over 2. And sine squared is also 1 minus cosine of 2x over 2. So one thing I'm going to do, the denominator, I'll have a 2 times a 2, which is going to give me a 4. Or in other words, I'll have a quarter that I can take out of everybody. So I'll have a 1 minus cos 2x times itself. And now I'll just multiply that all out. So I'll have that quarter on the outside, and I'll have a 1 times 1, 1 minus cos 2x, and another minus cos 2x times 1, giving me minus 2 cos 2x's. And then I'll have minus cos 2x times itself. I'll have cos squared 2x. Okay, so we've reduced our powers. We started off with power of 4, and now we have our highest power here is a power of 2. But again, I could just use my power-reducing formula, this time for cosine squared. One thing I just want to mention before we do that, and I'm going to slide back to the previous slide for a moment. For these power-reducing formulas, of course, if the number that's inside the squared function here is not just theta, if it was, for example, cosine squared of 4 theta, well then you would double the angle to have 8 theta once you've used your power-reducing formula. Or if it had been cosine of 5 theta, then inside the power-reducing formula it would be a 10 theta. Whatever the angle is that we have for the cosine squared, it's double that angle for the cosine squared formula. So I'm going to rewrite what I just had. And now let's expand that cosine squared of 2x using my power reducing formula one more time. So the formula for cosine squared is that we should have 1 plus cosine of double that angle. So since my angle was 2x, then I should have cosine of 4x and all over 2. I'm going to do a little bit of cleaning up here just to make things a little bit nicer, and then I will finish it all off in one last step. So first thing I'm going to do is just say that for that second last bit that I have here, this 1 plus cosine 4x over 2, I can split that into 1 over 2 and cosine of 4x over 2, or in other words, I can split it into a 1/2 and a cosine of 4x over 2. So I'm going to just do a little last bit of cleaning up here. I don't have enough room to fit all my writing in, so I'll just say it out loud. I'll start off by saying that 1 plus 1/2 is 3/2, and 3/2, when I multiply it by that quarter, gives me 3/8. The second term that I'm going to have, I have this minus 2 cos 2x, and when I multiply it by a quarter, I get minus cos 2x over 4, which is the same thing as minus cos 2x over 2. And then for the last term that I'm going to have, that's that cosine of 4x over 2, and multiplied by a quarter is going to give me cosine of 4x over 8. So we started off with something that had the highest power being power of 4, but I've managed to rewrite it so that I've got a constant term and a cos 2x term and a cos 4x term, but I have no powers higher than a power of 1 on any of those things. So there we go. I've used my power reducing formulas.